Okay. Hello, hello. It is 3 o'clock. It is time to, for real, start this live stream. I don't know if anybody will quote unquote attend, but that is totally okay because we're just getting off the ground with this. I'm Sam, this is Diego, and I have positioned the camera so that you can see Diego most of the time. Um, you can pretend he's talking too if you want. And today we're going to try to do a few problems that have to do with buffers. There we go. Yes, that drawing worked. Buffers. So I started answering this question, but maybe I'll just like erase my previous answers here and we can do this together. So it is asking us why the pair of ammonium chloride and sodium hydroxide can be used for a buffer, but the pair of ammonia and the same strong base, sodium hydroxide, cannot be used for a buffer. So first off, it might be good to talk about what even is a buffer. Essentially, a buffer is a conjugate acid and base pair that are at concentrations near the pKa of the acid, so that about half of both, or sorry, about half of the total population of the pair is in the acid form and the other half is in the base form. So if there are some slight additions of acid or base to the solution, the pH will only change slightly. So the crucial part here for what makes a buffer is this right here. You need a conjugate acid and base pair. We can talk about and look at the details of all this stuff more soon, but that's what we're going to need to make a buffer. So let's talk about what happens when we actually dissolve all this stuff. In both cases, the NaOH, the sodium hydroxide, when that goes into water, that fully dissociates into a spectator sodium cation and our very basic hydroxide anion right here. So that's happening in both cases. In both cases, we get, well, really, that's the strong base. Let's call it this up here. We have a strong base in both cases that is going to create a lot of hydroxide ion. In fact, complete dissociation. But in this case, we have ammonia, which is known as a weak base. And here we have ammonium chloride. So let's look at our yellow case, our ammonium chloride first. So this will also essentially completely dissociate within reason to ammonium cation and chloride anion. And the chloride anion and the sodium cation are both spectator ions. They're super stable. They're just going to hang out, maybe form a salt with each other to have some fun. These are the active agents here that we're actually talking about. We've got the ammonium cation and the hydro. And again, this is going to create a buffer because we have our weak acid here and our strong base here. The base is going to take one of those protons, or you could think of it as the acid gives the proton to the base. Either way, this is going to result in some ammonia and water. Now, if you have a lot of this and less of that, then you're going to end up using up all of your hydroxide, but you'll still have some of your ammonium left over. If you still have some of your ammonium left over, and then you just created some ammonia, that is a conjugate acid and base pair. This is why this does work as a buffer. So again, what's happening is the NaOH is converting some of the NH4 into NH3, ammonium into ammonia, and that creates the buffer pair. That is why this first pair that is highlighted in yellow can be used as a buffer. So in the other case, make this stuff all small here. There we go. Ammonia, NH3, if anything, is a base itself already. It's a weak base. So when that goes into water, if anything, it becomes NH4 itself. It's conjugate acid. The water having been H2O just gave one of the H's to the ammonia and is now OH minus. So that's going to happen. So if we add more OH minus, you're not going to successfully, let's say that we had combined these. We take this OH minus, doodly-doo, over here, and let's say it succeeded at taking one of those protons. Then you would have H2O and an amide ion, 2 lone pairs, negative charge, extremely basic, super proton hungry. So you might get this for a very, very brief microsecond, millisecond, nanosecond, something like that. But that amide is going to take that proton right back. So fundamentally, you're not going to end up in any significant way based on combining those two things with a population of conjugate acid and base pairs that can function as a buffer. So that's probably a not expertly phrased take on it. And hopefully it was not confusing, but what we can definitely say is that if you're using a strong base and you combine it with a weak acid, you can get a buffer. A weak acid plus a strong base, again, if the quantities work out, those are going to come together, as we saw in our first example, this one, to create that weak base and leftover weak acid buffer pair. However, if you go in with a weak base and a strong base, then you cannot create your buffer pair because you will just have lots of base. And every time this weak base tries to create its conjugate acid, as is drawn out right here, if you've added hydroxide, it's going to take that from it, so it can be water. And you're just going to end up with more of this. So the strong base, if you combine it with a weak base, will essentially consume all of the conjugate acid that the weak base creates. And so you don't get a buffer, you just have lots of base. So, cool. Let's check out the next question. So I have a list of questions, and we're just going to try them one at a time here. If anybody was here, I would say let me know if you have any questions. But if you're ever watching this video in the future, and you have questions, I suppose attempt to ask them. Like maybe in some sort of comment section or something. So, Question number 2, aka 79, for the second one that we're going to look at here. Why does pH not change significantly when a small amount of acid or base is added to a solution that contains equal amounts of NH3 and NH4Cl? So we just talked about essentially what's going on here. In this case, we're not using a strong base or a strong acid to create the buffer system. We're not doing that. We're just making our own, just starting right out with a good buffer. We have ammonia and ammonium chloride just like before. Ammonium chloride, when it goes into water, will dissociate. The chloride is a spectator ion we're not going to think about. So here it is. We have our buffer system right here. And if they're in equal amounts, then they're at some pH that I would imagine is probably pretty close to the pKa. We could calculate that in a sec. But you have both of these out here and you put in, let's say, a few drops of base, whatever kind of base it is. It could be a strong base, a weak base, just some. It's a small amount. Whatever it is, it's not a lot of it. And what's this base going to do? The electrons on this base are going to look at this proton over here and be like, hey, could you give me that? Right? And then we're going to have NH3 from when this ammonium lost that proton. And we're going to have this base that has now become its conjugate acid based on the way I drew it. I guess it has a proton on its head now. And by that same token, had we added, oh, let's not forget, we have this other NH3 also. Like this one didn't go anywhere. So now you just have more NH3. And I mean, depending on the amount of stuff, you'd still have NH4 plus there as well. I just figured I should throw that in. Okay, so let's say on the other hand, we'd added an acid. You see where this is going. Let's use green for this one. So an acid shows up to the party with its own proton. And in this case, there's a lone pair right here on this nitrogen in the ammonia that's looking at that proton on the acid and thinking, hey, maybe you should hang out with me, right? And next thing we know, now we have the conjugate base of the acid with its lone pair there, and we just created more ammonia, right? I'll write it in green, as if that's logical. It might be. Okay. So, and again, we already had some, so there's just more of it. And as long as we're only putting a small amount of the base or the acid in there, you're only going to slightly affect how much ammonium and ammonia there are in there. And so one more note on that, if you think about things in terms of Henderson-Hasselbalch, then if we're talking about pKa and not pKb, then it's the log of the ratio of the concentrations of, to use the same nomenclature I had up there, the conjugate base, the acid minus, I should probably have a minus on here, huh? Okay. Over the acid that you started with, H acid. So for this actual case here, that particular term is the log of the ratio of ammonia to ammonium. And so here's the point. Whatever the numbers are, and we could work out the numbers, but let's just not even bother with that for a sec. As long as this ratio barely changes, then the log of that ratio will barely change. If the log of that ratio barely changes, then pKa plus the log of that ratio barely changes. Therefore, the pH barely changes. We're about to do examples that use numbers of that. Of course, this right here was the Henderson-Hasselbalch. I hope I'm not accidentally misspelling that. And the Henderson-Hasselbalch only applies with a small amount of changing stuff. If you have a big change, you can't use this. You have to do something more complicated. But if we're talking about a small change, and especially if we were already near our pKa, meaning that this ratio, if this ratio right here was close to 1, which it is because we start out with equal amounts, then when we change those equal amounts by a small amount, then the log term will be very small itself. Small change, small log term. Okay, I probably had explained that well and then I made it too complicated or not complicated enough. I don't know. I don't have anyone in here to give me feedback. Again, if you happen to be watching this in the future and is some sort of situation where you can give me comments, including if we're like hanging out and I'm like, hey, watch this video and give me comments in person. Now would be the time to do it. So I'm just going to pause for like 1 minute so you can do that. And I definitely meant minute in a figurative sense because I don't want to actually sit here for a minute. So there we go. Paused a minute. That's the next question. The rest of these are much more numbers-y. Those first two were more on the concept side of things. So let's get into the numbers side of things. So what is even going on here? Let's look at a few things. We're given a Ka first off. So right off the bat, we know that we're talking about acid dissociation. We know that, oh, sorry, Diego. Got you out of the shot. Okay, there we go. That whatever's going on, we're going to have some sort of acid that is going to go into water and it's going to produce a proton that's going to latch onto the water producing hydronium ion. And, you know, interchangeably, we will talk about the concentration of it as either that or that. And then we're going to also have the conjugate base as such. Just as easily could have named this something else, but there's our name. So let's look at what we've got here. This must be our acid. Yep. There's the water. Yep. Here's our hydronium. Yep. And there's our conjugate base. So let's do a rice table. Now, this might be an X is small situation. I'm not sure right now, but I'm going to just do it as if X isn't small. Now, one thing that's pretty convenient for acid-base stuff is it's basically always one-to-one stoichiometry. So that's going to make this convenient. Even if it's a polyprotic acid, I believe we would look at each step as its own reaction, each deprotonation as its own reaction, so that our multiple Ka values are meaningful. So by that token, we don't have to think about stoichiometry at all. Plus NO. I probably just could have used the one they had, but here we go. And let's use the magic of computers to move this out of the way. Oh, Diego just heard something. Diego, don't leave us. Oh no, that didn't go well. Well, I'm just gonna erase this part. Okay, there we go. So everything's just gonna happen by one. We know that initially, so this is our reaction. Our initial situation here is that we've got, let's zoom in. Let's zoom in on this a little bit. Our initial concentration, 0.75 molar. I'm going to be lazy about units. Our initial concentration of hydronium is nothing. Our initial concentration, of course, sodium nitrate goes into solution and the sodium cation goes off and is a spectator that we don't care about. The nitrate's right there, right? So we're going to assume that all of that, unless we're past the saturation point, this is going to have very high solubility based on our solubility laws, different topic altogether, but clearly very related. So as long as we haven't supersaturated, all of this 0.03 molar of sodium nitrate is going to become nitrate. So that is why it is legitimate to say that that is the initial concentration of nitrate. Water's a liquid. We don't deal with liquids and solids in these rice tables. They're not part of the equilibrium expression due to activity with our products, right, over reactants. We only include ions and gases in our equilibrium expression. Therefore, we don't care about water. It's just water. There it is. Maybe I should have done that in blue. Let's highlight that in blue. It's not going to look water-like. I'll do better next time. Actually, it does look kind of water-like. It's kind of cool. All right. Yeah, okay. So, when these two liquids, or these two solutions, the nitric acid, or sorry, that's nitrous acid, I believe. When the nitrous acid and the sodium nitrate combine, there will be some change. Some amount of this proton right here is going to come off and go into water and become the hydronium ion. That's X. That same amount is going to become hydronium ion. When this happens, we're also going to get an increase in the amount of nitrate. That's going to go up by X. And that change is going to happen until equilibrium occurs. So that's our change. And then we're going to reach equilibrium. I'm going to maybe write those words better later. And these will be our values at equilibrium. Okay. So there we go. So at equilibrium, we can have our equilibrium mass action expression, which is always, as I noted here, products over reactants. If there were stoichiometric coefficients, we'd raise these things to them, but there are not. So our products are these guys, these ions right here, hydronium and nitrate. And at equilibrium, the concentrations of those are these two things. So we're going to have X, which is the concentration of hydronium, and keep that in mind for later. And then we're going to have 0.03 plus X is the concentration of nitrate. And our reactants, again, water, we just kind of ignore this whole time. There's so much of it. And the activity of it is just, it's the solvents, there's so much stuff, just water. We're just not thinking about it. Okay. But here we are thinking about the fact that this is the concentration of our product. So that's Ka, and we're also told that Ka equals a number based on experimental evidence. So it would be totally wise to proceed accordingly. So let's just say, because again, Ka equals 4.5 times 10 to the minus fifth. We're given that information. So therefore, I'm just going to swap that in this algebraic expression, x, and I could keep using brackets, but I'm going to switch to parentheses to just make my algebra flow faster. Doesn't really make a difference. I can just be like a little more fast. The brackets are the way to discuss concentration, but right now I'm just solving for x. And now we're going to just multiply both sides by the denominator right here. We're just going to multiply both sides by that. So now we're going to have 4.5 times that denominator is going to equal x times 0.03 plus x. So if you've done any of these problems recently, you know where this is going. Again, we maybe could do an x is small approximation, and maybe we'll circle back and do that and see how much of a difference it makes. But for the moment, I'm doing it in the let's just figure out exactly what x is fashion that's going to involve the quadratic equation. So let's multiply out both sides. Grab the old TI-84 here. 4.5 times 10 to the minus fifth times 0.075 equals 3.375 times 10 to the minus 6. So we've got 3.375 times 10 to the minus 6th. And then the 4.5 times 10 to the minus 5th just multiplies by the x straight up. When we distribute that, okay, so that's a term. That's a term. That is the left side of the equation as we're rolling with it. Now we're just going to distribute the x through there as well, right? We just distributed that. Now we're going to distribute the x. We're going to get 0.03 plus x plus x squared. Okay, so now I'm just going to clean this up. I know I'm going for a quadratic equation here. So I'm going to flip sides first off. I'm going to say that x squared plus 0.03x equals this whole deal right here, which I'm just going to not change for a sec. Okay. Anytime you're trying to solve a quadratic, of course, you want to get this form. You want to have an x squared term, an x term, and a nothing x term with some sort of a, b, and c coefficients, and set it equal to 0, and then you can use your quadratic formula to solve for x. I think that's right. The thing is, I just use an online calculator to solve the quadratic equation because when you're working with numbers that look like this, it's so easy to mess up when you do the quadratic yourself. So, and I always forget if I should have extended that all the way there. I need to just like learn that. Anyway, later we'll do that. This is not a quadratic equation lesson, even though that is crucial for what we're doing. So let's keep doing it. So now we're going to just add this term to both sides and then subtract that term from both sides. And that will set this right side equal to 0. Now this is an x term. Here's an x term. So those are going to combine. We're going to have x squared, and this is minus on this side. So I'm adding it. So I already had this. And 4.5 times 10 to the minus fifth is the same thing as, right? Because we had 1, and then it starts there, and we go 1 spot, 2 spot, 3 spot, 4 spot, 5 spot. Yes, so 4 zeros, 4, 5. So 1, 0, 2, 0, 3, 0, 4, 0, 4, 5. You could have put that in your calculator and gotten that, but there you go. That's how you might be able to do that in your head. And then this term without an x is positive on this side, so we're going to have to subtract it. to get rid of it from the left and move it to the right. So there we go. Hey, buddy. And that equals 0. And then we're going to plug this in to a quadratic equation solver, which I already did earlier. So I'm not going to do it again right now. But I encourage you to do it. And since there's nobody here live, if you're actually watching this, you could, hey, no, don't bite me. Don't bite me. Claws in your paws. Hey, claws in paws. Uh, okay, I just talked to my cat long enough for you to have found a quadratic equation solver. So yes, if you're watching this at some point in the future and you really want to be participating, you could pause it and either solve the quadratic equation yourself using the fact that a equals 1, b equals 0.03, and c equals negative 3.375. By the way, you might be thinking, aren't those too many digits? Shouldn't our significant figures be like 2 sig figs, 2 sig figs, 2 sig figs? Yes, at the end, we'll account for that. While we're working, though, might as well have too much detail. Either way, you're back. If you ever went to go find this, you have used a quadratic equation solver. There's this one called like calculator soup that I use a lot. That's good. I think that's the top one that Google shows you. So however you solved it, you should get a positive and negative possible answer for x. Negative concentration does not make sense. So we're going to not use the negative answer. We're going to use the positive answer. If you got 2 negative answers, or if you got an answer that involves an imaginary number, then you put something in your calculator wrong or something into the quadratic equation solver incorrectly. And revisit your work and figure out what you did, would be my advice. Okay, so this is what I got when I practiced these problems last night. Or that's what the quad solver told me. That's x. Okay, great, we solved for x. Wait, what class is this? This is chemistry. Why do we care about x? This is not algebra. X is the equilibrium concentration of hydronium ion. It's the concentration of hydronium at equilibrium. That is what X even is. So we just found the concentration of hydronium. And this question asked us for the concentration of hydronium. Oh, cool. I was going to take it one more step and find the pH. And I actually did that when I worked on this last night, but we're actually done. This is what the question asked for. So it's a concentration. It should be molar, right? It'd be good to have a unit on there. Let's gut check that that's the right units. It is because the numbers we started with were molar. So we're good on that. I did mention that we should consider significant figures, and we should because that answer is a little silly looking. So let's just make this a better, yeah, we'll do it in blue, sure, let's do it in blue. Better looking answer. This is 1.11915 blah 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 times 10 to the minus, the decimals here, 1, 1, 2, 3, 4, 10 to the minus 4. And we only had 2 sig figs, so I could round this up to 2, but that's still 1.1. So we're just going to say 1.1 times 10 to the minus 4 molar equals the concentration of hydronium ions in the conditions that we were provided with. And there we go. That's the answer for that. Cool. So I know Diego's very curious about the stylus, but I'll let you help with the next one. Okay. So we have a few more, and I'm supposed to do this for an hour. I think we can make this happen. And that is there. And here we go. So this is basically the exact same thing as the last question, except for what? Anybody? Anybody? Diego is the only person who's here with me. Claws in your paws, buddy. But he knew I was talking about him. So he just wanted to show me that by digging his razor sharp talons into my leg. I don't think cats officially have talons. Actually, I do think talons is probably very bird specific. Anyhow, here we are with not a Ka given to us this time. This time we're given a Kb. So the definition of Kb is just like Ka, except for our generic chemical equation that we're talking about here is we have a base that has a lone pair, and it would love a hydrogen. And so there's some water, and that base says, hello, water, can I have one of your protons? And so that happens. There's some sort of back and forth equilibrium going on. You get your base with the proton on it. This is aqueous, by the way. You get your OH minus from when that water, that's got a charge, that's got a charge. OH minus from when the water lost its proton. So our Kb expression is products over reactants. And we don't count liquid in our expression, so it turns into the concentration of base plus, so the conjugate base, sorry, the conjugate acid, I apologize for misspeaking there. Oh, not plus, sorry, times hydroxide over your initial base, which may or may not have a minus charge case by case, but we're going to call it that. And think of it as neutral for now. So this is what the Kb expression means. And that ratio, if we're at equilibrium, equals that. So let's just use their equation this time. And we're going to identify that in this case, base equals NH3, ammonia. The H base, the conjugate acid, is ammonium. Just like in previous problems here, the ammonia has a lone pair. It would love to grab a proton, and that's what it does. So this time I'm just going to use the printout for our rice table. Now, let me zoom in a little bit better on that. It looks like we're starting out with 1.25 molar of ammonia. That is going to go away because it becomes a different thing. When it becomes that, when it gains a proton, it becomes a different thing. So the amount of just NH3 ammonia, once we're at equilibrium, will have started at 1.5, but it will have lost some amount. Once again, water, we're not thinking about. And our ammonia, now this is another situation. This goes into water. Unless we are at supersaturation levels, then these split up completely. And so the fact that you started with 0.78 of this salt, the ammonium nitrate salt, you can just one-to-one that it's that same concentration of ammonium to start with. And that is going to gain however much ammonia goes away by stealing a proton, that's how much new ammonium will be created. That's X. It's a one-to-one stoichiometry. And then hydroxide, in theory, when we very first started, this started out as nothing. And then for every time an ammonium gets created by stealing a proton from the water, what remains of the water is the hydroxide. So before anything happens, you don't have any hydroxide. But then every time that this goes down, you gain a hydroxide. So there we go. So our Kb this time is going to equal products over reactants, conjugate acid, and hydroxide over our starting base concentration. You know, concentration. I'm admittedly being a bit sloppy. So this is from here the exact same thing as last time, but like let's do it anyway. So we've got 1.25 and we've been told that this equals this based on experimentation. So time for some more fun with algebra, and maybe I'll kind of do some of these steps at the same time here. Like first off, let's go ahead and distribute, multiplicatively distribute that in one move, and we're also going to multiply both sides by this in the other move. So we're going to have 1.8, and I'm going to flip the sides, times 10 to the minus fifth times 1.25 minus x equals x squared, right? Because x times x squared plus 0.78x. Okay, so now let's go ahead and distribute the 1.8 times 10 to the minus fifth into this term, which I did this last night, but let's just do it again. Make sure I get the same answer again. 1.8 times 10 to the minus fifth times 1.25. By the way, 1.25 is kind of like a big concentration. That's like a lot, by the way. So we're going to expect, what's this question even asking? This question is, just like the last question was asking for concentration of hydronium, this one's asking for concentration of hydroxide. And we have a lot of base, a big concentration. So we're going to expect a pretty big concentration of hydroxide. Maybe I'll figure out the pH too. But in the meantime, we have 1.8 times 10 to the minus fifth times 1.25, which is 2. Oops, I accidentally changed pen colors, but we're going to roll with it. That's what happens when you multiply that times that. And we still have minus 1.8 times 10 to the minus fifth x. It's going to equal x squared plus this. Now we're going to do the exact same thing as the last problem and combine these sides together and set one side equal to 0 plus 0.78, and then 10 to the minus fifth, so that would be like 4 zeros, 18x. And then I have to take the 2.25 times 10 to the minus fifth and move it to the same side as my x squared, which I've flipped again. So I have to subtract it from both sides to move it, equals 0. So now, once again, we're basically just ready to quadraticize this here with A equals 1, B equals 0.78, doop-a-doop, and C equals this very small number here. Okay. And then you put that into your quadratic equation, or you have a robot do it for you, or you have your cat do it for you. Your quadratic equation. Sorry, I'm just going to try to write that. Quadratic? Quadratic? All right, I'm going to keep thinking about that. The quad solver tells us that x in this case equals 2.8844 times 10 to the minus fifth. And once again, what even is x? We had said that x is the concentration of hydronium at equilibrium, which is what this question is asking for. So the only thing that really remains is to note that we're given actually 3 significant figures here, but only 2 here and only 2 here. So let's just be proper, diligent little students and say that the concentration of hydronium at equilibrium, which the question didn't explicitly say that, but it very much implies it, is really 2.9 times 10 to the minus fifth molar. And that is what they asked. And that's actually like kind of a lot. Like if you put your hand in that, you probably would not be happy. That would probably steal a lot of protons from your hand. So there we go. That's the answer to that one. And obviously, I do not recommend sticking your hand into an acid or base solution. They were both very bad for you. All right, we only have a few more, and we have some minutes, and maybe we can get this all done. Oh no, but my cat left. Dude, no. You have to be here. You're the star of the show. Come back. He didn't like that I was moving. No, no, come back. Come here. Come on. All right. We're going to just lure the cat in by just doing chemistry. And he's going to come back. Right? Right, Diego? I hope he does. But if he definitely usually makes a point. Let's actually just move this all down. He usually makes a point of being on my lap anytime I'm sitting at the computer. So I do not know what's going on with him now. But here we go. Let's do this one. Okay. So in this case, one thing that we have to do is find a particular piece of information. Because let's just look at this for a second. It's asked here, and now that my cat's on my lap, I'll actually get my face in the shot. So I don't think this is like the ideal camera setup here. I really did have it mainly to feature Diego, who's now bailed on me. But no, he's just right over there. He just wanted to groom more. Um, but anyway, let's just roll with this. And in this case, we can't really like say anything meaningful about any of this if we don't have a Ka or maybe a Kb, because these are experimentally determined constants that pertain to these substances from the real world. And without that, we would just literally be making something up. So I looked in the appendix of the textbook for this class that PSU is using, which is, should probably have the link to it, but it's like Chem Libre. It's a free open source textbook. You probably know about it. Maybe I'll find the link in a sec here. But more importantly, I got the Ka that we need from the appendix of that book, Appendix H. And aforementioned Ka, there it is this, oh, pen? Yeah, there we go. This is what Appendix H of the textbook says. The Ka of a thing that I'm about to tell you about. And let's just point out that if Appendix H of the book says that, that probably is the Ka. Hopefully any Ka table will tell you the same number, because this should be a universal truth about the acid dissociation of this phosphoric acid. That's what we're talking about. The Ka of phosphoric acid. If you are, we should note, we're talking about standard conditions, so like 25 degrees Celsius, 1 atmosphere of pressure, etc. If you're in a high or low temperature, high or low pressure situation, the stuff might be different. But in normal conditions, phosphoric acid will dissociate accordingly, and again, you'll have your A minus product and your H plus, which is the same thing as H3O plus, and you'll have some of your original acid, and that's phosphoric acid. What is phosphoric acid? Phosphoric acid is PO4H3. It's triprotic. It has up to 3 protons to give away. It could give away a proton. Some base comes along for some reason, it gives away a proton, and now it's H2PO4. Nothing changed about the number of oxygens or phosphoruses there, but it does have a negative charge now. It's got an extra pair of electrons because the proton left and left behind some electrons. And then that can give away a proton. And then you're going to have HPO4 2 minus, and that can even give away a proton, you know, in certain conditions. And you're going to have HPO4 3 minus in proton, right? So this is phosphoric acid. This is phosphorus acid. This is, I believe, hypophosphorus acid. Is that right? And then this is called a phosphate. That's definitely a phosphate. My possible errors in nomenclature aside, what we're interested in here is that, right? This is what they have told us, because this is yet another case of KH2PO4, or potassium dihydro, I bet is how some people would call it, phosphate. That goes into water and it dissociates into K plus, spectator ion that we don't care about, and H2PO4 minus, which is the conjugate base. So H3PO4, oh, there's so many arrows, is this weak acid. It's a very strong weak acid. Times 10 to the minus 3 here is a very strong weak acid, but it's a weak acid. So this is what's going on. Just part of what this question is all about is that we have to do a little bit more interpretation of the question, because we had to piece together that this meant this. We had to piece together that phosphoric acid was H3PO4. I mean, it wasn't that hard, but we had to do that. And you would have had to look up this number if you weren't given it. Otherwise, you can't do this. You would have had to find the Ka of phosphoric acid in order to do this. Now, the other thing to consider is that they didn't give us molarity. They gave us moles and a volume. So we're going to actually have to calculate our concentration. So our concentration of phosphoric acid, which I'm going to write like this from now on, is going to equal the given moles Diego's still here, by the way. He's just right over there, but he just had enough lap time for today, I guess. I did a little practice session getting this whole Twitch thing running, and so he was on my lap that whole time, so that must have maxed him out. Okay, so basically we're dividing by a half, which is the same thing as multiplying by 2. So the concentration of phosphoric acid here is going to be 0.155 times 2, which I like to unnecessarily do math in my head sometimes. So that is 3. I think that would be 0.31. That seem right? That is right. Molar. So I actually should have written that not up a little. Let's write it on the line. It's 0.31 molar is the concentration, is our initial concentration of phosphoric acid, and our initial concentration of the conjugate base, dihydrogen phosphate, anion. Oops, that should probably be in there. Well, we're just going to do the exact same thing. Once again, the volume's the same. We've been told that it's going to be the same half-liter solution in both cases. Oops, there we go. And we're starting in this case with this many moles. That one hopefully is very easy to do in the old noggin. 2 times 0.25 equals 0.5. And just for fun, let's include that molar. So that's the concentration of our conjugate base. So what are we looking for? pH. That means we need to find H plus or hydronium. And then we're going to take the negative log of that, and that's going to equal the pH. So, and this is the x we want. We want to figure out what that x is. So let's do a rice table. I think we need to. Do we need to do a rice table? Yeah, we should do a rice table. Okay. So we have our H3PO4 is going to dissociate with water, which, as we've discussed, not in the rice table, so let's write it like this, to become H2PO4 2 minus, the conjugate base, and H3O plus, the hydronium ion. And that's our reaction. Our initial concentration, we just figured this out for both of these based on the given information. Our initial concentration is 0.31 molar and 0.50 molar, and we start out with, theoretically, no hydronium. And then this goes down by x, this goes up by x, this goes up by x, and we end up with 0.31 minus x, and 0.5 plus x. Sorry, that was a little sloppy. There we go. So now we can solve for x because we had looked up that the Ka was 7.5. We looked this up. 7.5 times 10 to the minus fifth. Oh, sorry. My bad. 10 to the minus third. And we know that that is equal to, you know, any old Ka expression. It's always the same. Ka. There's the expression. So conjugate base times hydronium over weak acid. And we're going to basically take this, multiply both sides by that. So we're going to multiply that by that. We're going to distribute this through that. That gets multiplied there. When we multiply both sides by this, that means that this gets multiplied by that, and this gets multiplied by that. And so after doing that, and I'm going to flip sides, so I'll scroll down here. So the next iteration of this, hopefully hopefully everybody and anybody is following along with this algebra. So I always like to get my x squared on one side, so I'm going to flip the sides. X squared plus 0.5x is going to equal, we have to do 0.75 times 10 to the minus third times 0.31, which I entered incorrectly apparently. Let me try that again. 7.5 times 10 to the minus third times 0.31. There we go. 0.0022325 minus 7.5 times 10 to the minus third times x equals that. Right? And now we just combine terms. So we're going to add this to both sides and subtract that from both sides. Same deal I've done before. 7.5 times 10 to the minus third, 1, 2, 3. That's 2 zeros. So we got 1, 2 zeros, 7, 5. X, and then minus that whole mumbo jumbo. And that whole thing is now equal to 0 because I moved everything to the same side. Quadratic equation, solve. You rock that, and you get that x equals 0.00454. That's actually a very large concentration of hydronium ions. And of course, we consider that to be interchangeable with just the concentration of protons. And pH, of course, is the negative log of the concentration of protons. Dude, wait, that should be like, oh man, totally. I was trying to be all precise right there. Okay. And if you take the negative log of this, which is 4.54 times 10 to the minus 1, 2, 3, you get that the pH equals 2.34. And I always love it when numbers are in order like that. 2.34 is the pH of phosphoric acid. When you mix phosphoric acid with its conjugate base at these concentrations, it has a quite low pH, which totally makes sense. We would expect phosphoric acid, which again has this Ka that is times 10 to the minus 3. That's actually a pretty big number for a Ka. That's a pretty low and pretty acidic. It's quite acidic, right? Makes sense. It's phosphoric acid. Okay, let's see. This live stream has been going for over an hour, so I could call it quits. But let's see. We had 2 problems left, and I think what I'm gonna do, since nobody showed up on the live stream anyway, is I'm gonna maybe do these 2 problems as a separate video. But I don't know how this went. If you watched, then cool. Thank you for watching. Feel free to attempt to communicate, and we'll be posting more of these. So study hard, have fun, always write your units, and see you in the next one.